Welcome to our discussion on relative motion. First, we're going to talk about relative motion in one dimension. Up until this point in the course, we've been describing the position and the velocity of an object with reference to some fixed point, such as the ground. On occasion, we will see objects that are moving relative to a moving observer. For example, suppose that you're in a train and you're walking down the aisle towards the front of the train, and the train itself is also moving. Your speed relative to, say, a passenger sitting on the train would be different, say, from a person that is on the ground watching you move as well. So we say that motion is relative. When we say, for example, what is the velocity of this passenger walking down the aisle on the train? It may not be like a single answer because it really depends on whose perspective, whether it's from the ground or whether it's from, say, someone sitting on the train watching you move. So really, the motion is relative to the observer. For each observer, we assume that the observer is equipped with, in principle, a meter stick so that we can measure your horizontal, vertical, and positions, X, Y, and Z, for example, and the stopwatch so you can measure the time. And we call that the frame of reference. A frame of reference is a coordinate system with a timer. In this example, number 5, we can generalize it by establishing a frame of reference, say, for the train. So here I've drawn a coordinate system with x sub train and y sub train. And suppose we have this passenger, which we'll label P for passenger. Then we can discuss the passenger's position at this point P relative to the moving train. And we'll assume that the moving train has some reference point or origin, which I'll label it as O sub t. The distance between the passenger and this established frame of reference we'll write as x with a subscript p slash t. So this is really the position x of the passenger relative to the train. We can also say that there is a velocity v of the passenger p relative to the train. Now you'll notice that I use backslashes. It really doesn't matter whether you use backslashes. You could, if you'd like, not use backslashes and just use v sub p and then t, or you could use a comma here. So this is read as the velocity of the passenger p relative to the train t. Sometimes we like to use these backslashes, and I'll show a reason why later on. I personally don't mind whether you use the slashes or not. I just want you to be consistent and show your work clearly. So let's answer part A. We're asking how fast would the passenger be walking relative to the train. So you can see that there's passenger and train. So we're going to be labeling passenger P and train T. Therefore, we're asking for the velocity of the passenger relative to the train, which is really, if you look at the problem, that person is walking at a speed of 2 meters per second down the aisle of the train. So that's 2 meters per second. And we're going to write positive 2 meters per second because we're going to be assuming to the right is positive along our x-axis. In part B, we're asked how fast is the train, T, moving relative to the ground, G. So in this case, we will have to establish another frame of reference for the ground, G, with origin O sub G. And there's my coordinate axis with the origin located right here. And in the way that we did it earlier with the coordinate system for the train, we could also measure the position of the train relative to the ground. I'm going to label that distance as x, the position x of the train. So we have the subscript t relative to the ground. We could also describe the velocity of the train itself relative to the ground observer. And that is given in the problem as 9 meters per second. So we will label that as the velocity v of the train t relative to the ground sub g. Thus, our answer to this question B, how fast is the train moving relative to the ground, that is given as the velocity v of the train relative to the ground is equal to positive 9 meters per second. Again, we're using positive because the train is moving to the right in our coordinate system, which is positive along our x-axis. Now let's move into part C, where we ask how fast is the passenger moving relative to the ground-based observer. Now, we could go into discussing how the positions can be added or subtracted to get this distance here, which I'll label as x of the passenger p relative to the ground. But what we're really looking at in this question is, what is the velocity of the passenger p relative to the ground? We're looking at the velocity in this case. Now, we know that the velocity of the train with respect to the ground is 9. We also know the velocity of the passenger with respect to the train is 2. What do you think the answer would be to find the velocity of the passenger p relative to the ground? What does your logic tell you? Well, hopefully, you're thinking of a possible equation to write. The velocity of the passenger relative to the ground is equivalent to the velocity of the passenger relative to the train plus the velocity of the train relative to the ground. So what you get in the end, if we substitute the velocity of the passenger with respect to the train, is 2 meters per second, positive 2, and the speed of the train relative to the ground is 9 meters per second, you get an answer of 11 meters per second to the right. And that hopefully makes sense to you without doing all of the subscript business. Notice since both velocities were to the right, which are positive, we added them to get our final velocity of the passenger with respect to the ground-based observer. What would happen if, say, the train were going instead, or maybe the passenger were instead going to the left at -2? So the passenger would be walking to the back of the train. How fast would that passenger seem to be going with respect to the ground-based observer? Now, hopefully you're looking at this and thinking, well, the answer would be simply -2 meters per second plus 9 meters per second, which would give you 7 meters per second. So if the train were moving to the opposite direction, then we would make that velocity now be negative because it's going towards the left. I know you're probably thinking at this point that this is a relatively straightforward problem, and you could probably do away with all this subscript business that I'm showing you. However, if we get into more complicated problems, the method of using subscripts can be quite helpful. For example, notice the order of the letters. If you look at it, I start with a P here, and I start with a P here. I end with a G here, and I end with my last term being a G. And then if I end with a T on my first term, then the next term starts with that. So there goes, you could think of it in terms of fractions. You could write, say, P over G is equal to P over T, then times T all over G. And the T's will cancel out, and so you get P over G equals P over G. So the ordering of the letters, or of the subscripts, can be quite handy. So notice if I had something more complicated, say with 3 different moving frames of references, like imagine this passenger was on a conveyor belt that was on a moving train, and then the observer was watching this person move on a conveyor belt that is moving with respect to a train that is moving with respect to the ground-based observer. Then you would have 3 different moving frames. So if you were looking at a situation where you have the velocity of the passenger with respect to some frame of reference A, you can go from P to C, then notice the C over here overlaps here to C, and then C to B, and then the B is then continue over here, and then the starting term matches with the starting term here, and the last letter here in the subscript ends up with the same last letter over here on the left side. So remembering this subscript rule will be very, very helpful, particularly when you get into more complicated problems. Also, another helpful rule is that if we were to reverse the subscripts, let's say we took the velocity of AB, that's going to be equivalent to the velocity of B relative to A. So it's the negative of that. That negative is very important. For example, let's say that this moving passenger in the train were to look outside the window and look at this ground-based observer. What would he see? Well, the velocity of the ground relative to the passenger would be equal to the velocity of the passenger relative to the ground, the negative of that. So in part C, we got an answer of 11 meters per second. But if you were looking at the velocity of the ground relative to the passenger, as he looks back through the window, it would be appearing to be a negative 11 meters per second from the passenger's perspective. He would be looking like he's going backwards at 11 meters per second. I know that you could probably just look at this problem and logically come up with the answers. But the reason I'm going through this very explicitly is as you go through more complicated problems, these rules down here at the bottom are particularly helpful. So just remember to review that, and that will help you quite a bit in the more complicated problems that we'll see.